The Republic P-47 Thunderbolt was not a pretty airplane. Other fighters had a kind of elegance to them: slim wings, narrow fuselage, the kind of silhouette that looked fast even sitting still on the runway. The P-47 looked like someone had designed a bathtub, given it a propeller, and then dared it to fly. It was wide. It was heavy. It was, by the standards of the men who flew it, the least graceful thing in the sky. But it was also nearly indestructible, and the pilots who came home in one understood the difference between beautiful and alive. The airplane carried 8.50 caliber machine guns and a Pratt & Whitney R-2800 engine that produced more than 2,000 horsepower, enough raw energy to vibrate the fillings loose from a man's teeth if he wasn't careful. The Germans took it seriously. The Japanese took it seriously. The pilots called it the Jug, which was short for Juggernaut, or maybe Jug because it looked like one, depending on who you asked and what kind of morning they'd had. By early 1944, the United States had thousands of them in the air over Europe. And by early 1944, the men responsible for keeping American bombers alive over Germany had a problem they couldn't quite solve. The problem was speed. Not at low altitude, down low, the Thunderbolt was a weapon. 8 guns, diving hard, it could tear through anything that crossed its path. The trouble was at 30,000 feet, where the Luftwaffe's best pilots flew their Focke-Wulf 190s and Messerschmitt 109GS with a kind of contemptuous ease, and where the P-47 began to run out of answers. Above a certain altitude, the Jug's performance ceiling became a genuine ceiling. The engine was producing power that simply wasn't translating into speed the way it should have. Pilots felt it. Commanders noticed it in the data. Engineers stared at the numbers and argued about whose problem it was. Nobody had a clean answer. There was a young engineer at the Curtiss-Wright Corporation named Thomas Harrigan who thought he knew why. He was 28 years old. He had studied aerodynamics at the Massachusetts Institute of Technology, which meant he understood the theory behind propeller behavior at high speeds in ways that most working engineers had never needed to think about. He also had the particular personality that seems to appear in certain young engineers, the kind that cannot let a problem rest simply because the people above him in the organization have decided it isn't worth pursuing. His idea was not complicated to state, even if it took considerable mathematics to prove. He believed the propeller blades were destroying themselves. Not literally, they weren't cracking or failing. But at high altitude, when the engine was running at maximum power and the propeller was spinning at high revolutions, the tips of the blades were moving through the air at speeds approaching the sound barrier. And at those speeds, the air stopped behaving the way aerodynamics textbooks said it should. The smooth flow of air over the blade surface broke down into something called compressibility shock, a kind of invisible wall that turned forward thrust into wasted energy, heat, and noise. The engine was producing all that horsepower and the blades were simply failing to convert it into speed. They were choking on their own velocity. The fix Harrigan proposed was a different blade shape. Standard propeller blades in 1944 were narrow and relatively uniform, the product of 20 years of careful engineering optimization that had settled into something close to doctrine. Nobody changed propeller blade profiles casually. The process of designing, testing, and certifying a new propeller geometry was expensive and slow, and the people who controlled that process had spent careers building confidence in the designs that existed. Harrigan wanted blades that were wider. Dramatically wider at the tip than anything then in production, almost paddle-shaped, which was eventually exactly what people called them. The wider chord at the tip would handle the high-speed airflow differently, distributing the aerodynamic load in a way that delayed the onset of compressibility shock and allowed the engine's power to actually reach the air as thrust rather than disappearing into turbulence. He wrote a memo. The memo did not change anything immediately. This is, in the history of engineering, approximately what always happens. The people who receive memos explaining that the current approach is wrong are rarely the people who are most enthusiastic about funding a replacement. Harrigan's supervisor read the memo, noted that it was theoretically interesting, and suggested that a more thorough study would be required before any development resources could be committed. The Army Air Force's Procurement Office received a version of the memo through channels that Harrigan had pushed it through by asking increasingly senior people to look at it, and they responded with language that translated roughly to, "We will consider this when we have time," which is not now. Harrigan kept working. He refined the blade geometry. He worked through the mathematics of how a wider chord would behave at different altitudes and air speeds. He found, buried in a set of intelligence reports that American analysts had compiled from captured German aeronautical research, some early German work on propeller profile modification that aligned with the direction he was going. He incorporated what was useful and discarded what wasn't. He built a case that was, by the middle of 1943, considerably stronger than the one he had started with. And then, slowly, through the kind of institutional process that feels agonizing to anyone watching it from the outside, things began to move. Curtiss Wright agreed to produce a prototype set of the wide-chord paddle blades. The agreement came with conditions and liability language that occupied a lawyer for nearly 3 weeks, and with a general atmosphere of institutional reluctance that Harrigan had learned to work around by that point. The prototype blades were machined to his specifications. A P-47D was designated for modification. A test pilot was assigned. The test pilot's name was Lieutenant Colonel Edwin Ferris. Ferris was from Alabama. He had learned to fly as a teenager, spent years crop dusting the flat agricultural land of the South before the war found him, and redirected his talents toward aircraft that moved considerably faster than anything carrying pesticide had any business doing. He had accumulated more hours in high-performance aircraft than almost anyone in the test program, and he had developed, over those years, the particular quality that made a good test pilot: the ability to sit inside a machine that was doing something unexpected and observe it with something close to scientific patience instead of panic. He was not especially interested in the engineering theory behind the modified blades. He was interested in what the airplane would do. He took the aircraft up on the morning of April 9, 1944. The air at altitude was cold and thin and extraordinarily clear. Ferris climbed through the lower atmosphere with the methodical patience of someone who understood that the interesting part came later. At 25,000 feet he ran the aircraft through its level flight test sequence, holding the throttle at specific positions and letting the instruments record what the airplane was doing. At full power in level flight, the indicated airspeed was already telling him something worth paying attention to. The numbers were better than they should have been. He climbed to 33,000 feet. The dive came next, a maximum effort dive with full power, the airframe loaded by gravity and acceleration in ways that made the structural engineers at Republic Aviation briefly reconsider their choice of profession every time a test like this ran. Ferris held the throttle forward. He held the aircraft in the dive. He watched the instruments. The airspeed indicator climbed past numbers the dial had been calibrated to reliably show, and kept going. Post-flight analysis combined the instrument data with radar tracking information from the ground station that had been following the aircraft. When the engineers put the numbers together, they arrived at a figure that required some verification before anyone was comfortable saying it out loud. The aircraft had reached approximately 470 miles per hour in the dive. Some accounts placed the figure higher. The precise number was disputed, as precise numbers always are when the instrumentation is operating at the edge of its reliable range and the people calculating the results have strong feelings about the outcome. But the general magnitude was not disputed. The P-47, fitted with Thomas Harrigan's wide-chord paddle blades, had posted a speed that made it one of the fastest propeller-driven aircraft in testing anywhere in the world at that moment. Ferris climbed out of the cockpit and handed his knee-board notes to the waiting engineers. The expression on his face was the expression of a man who has decided to be professionally restrained about something that has made him genuinely happy. He said a few words to Harrigan. The words were later slightly adjusted in the official documentation to match the formal register that military records prefer. The meaning, however, was clear. The production order was approved within 6 weeks. The wide-chord paddle blade entered service on the P-47M and P-47N variants, the fastest and most refined versions of the Thunderbolt that Republic Aviation ever produced. The M model was designed specifically for the European theater, built around a single operational requirement that had become urgent by late 1944, catching the German V-1 flying bombs that were crossing the English Channel and reaching London faster than most fighter aircraft could intercept them. The paddle blade gave the M model a top speed that made interception possible in ways it had not been before. The N model was built for the Pacific, where the distances involved in reaching Japanese targets required not just speed but endurance, a combination that the engineers at Republic managed by expanding the aircraft's fuel capacity while preserving the performance gains the new propeller had delivered. Pilots who flew the M and N models came back from those aircraft with opinions. The opinions were generally positive, expressed in the particular vocabulary that combat pilots develop for machines they trust. The aircraft felt different. It felt like it was finally using what the engine had always been trying to give it. At altitude, where earlier P-47s had run out of authority, the new variants held their speed with something that felt, to the men flying them, like confidence. Several German pilots who survived the war and were later interviewed about their experiences in the final year of the conflict described a change they had noticed in the performance of American fighters. The margin that had previously existed, the margin that allowed a Luftwaffe pilot to calculate an escape, to estimate whether a dive toward cloud cover would be enough, to decide that a particular engagement could be broken off and survived, had narrowed. Some described it as having essentially disappeared. The American fighters in 1945 were not the same aircraft as the American fighters in 1943, not in any way that mattered to someone trying to determine whether they would be alive at the end of an engagement. Part of that change was the Mustang and its extraordinary range. Part of it was pilot experience, accumulated over years of combat. Part of it was the simple arithmetic of German losses, fewer pilots, less fuel, older aircraft, deteriorating training programs that could no longer produce the quality of aviator the Luftwaffe had started the war with. And part of it, a real part, not a negligible one, was a propeller blade that a 28-year-old engineer had designed in the face of institutional indifference and pushed through production through sheer persistence. Thomas Harrigan received a commendation. It was the kind of commendation that acknowledged something important had happened without particularly dwelling on who had been wrong about it in the years before it happened. He was not featured prominently in the press coverage of American aviation achievements, which tended toward pilots and aircraft rather than the men who designed propeller geometry. He went back to his work, which continued to involve blade aerodynamics and continued to involve writing memos that took longer to get approved than the mathematics suggested they should. Edwin Ferris flew 11 more test programs before the war ended. He returned to Alabama when it was over. He did not, by the accounts of people who knew him, talk much about the April morning when he had taken a modified Thunderbolt to the edge of what a propeller-driven aircraft could do and brought it back with numbers that changed a production line. He was a man who had done many things worth talking about and seemed to feel that talking about them was not the point. The Thunderbolt itself, the whole line of them, from the earliest models to the final production variants, faded from prominence in the years after the war. The jet age arrived with a speed and certainty that made propeller-driven fighters feel almost immediately historical, and the P-47 became a museum piece before many of the men who had flown it in combat had finished adjusting to peacetime. Photographs of the aircraft look, to contemporary eyes, almost improbably large, that wide, blunt fuselage, that massive radial engine cowling, the heavy undercarriage built to absorb the weight of everything Republic had put into it. But the paddle blades on the late production models look, even in old photographs, subtly different from what came before. Wider at the tip. More deliberate in their geometry. The product of someone who had looked at a problem that other people had decided was not a problem and had refused to accept the consensus. The blades influenced propeller design for decades after the war. The principal Harrigan had demonstrated that wide-chord geometry could manage transonic tip effects in ways that narrow blades could not, moved from experimental to established, from heresy to curriculum. Aeronautical engineering students learned it as fact, in textbooks, without any particular reason to know that it had once been a memo that a supervisor had declined to act on. This is, in engineering history, also approximately what always happens. The jug never became elegant. It remained, to the end of its operational life, a machine that looked like it had been designed by someone who prioritized function over aesthetics with a kind of aggressive disregard for the opinions of anyone who felt otherwise. But in the last year of the war, fitted with blades that finally let it use what its engine had always been producing, it was something more useful than elegant. It was fast enough. And for the pilots who flew it into the thin cold air over Germany, and for the bombers they were protecting, and for the whole long and exhausting arithmetic of the air war over Europe, fast enough was exactly what was needed.